Thank you so much for the introduction. So let's get started. Okay. This is a very complicated name for saying let's combine zero-knowledge proofs in order to get the maximal advantages of each system. And I'm going to start a bit more accessible, just with the concept of a cryptographic proof. We're not going to dwell too much on it, but basically we have a prover, we have a statement, we have a witness, and we want to make a proof. What does that mean? This proof then gets fed into a verifier, and the verifier also needs access to the statement, and it's going to accept or reject. And in order for all of this to happen, we will also need some setup parameters. And to give you a flavor of what kind of statements and what kind of witnesses we can support, the verifier, for example, this is an example of strong authentication. You can imagine a server that has a big database of a lot of encrypted passwords and IDs, like national IDs, and maybe some other private information. When you want to authenticate, the server sends you a ciphertext. The statement is going to be me, the client. I know a witness such that this ciphertext is the encryption of the witness. And then the witness is going to be, in this case, like my password, my birth date, national ID, so something really stronger than just encrypting with a password. And then we send this proof, and the server decides whether he is going to authenticate or not. And the interesting thing is that, well, we want that the proof doesn't leak all this private data. And another example of cryptographic proof, which is actually going to be more relevant for this case, and it's a case in which we will not need secrecy, is outsourcing computation. So here the verifier is a weak machine. It sends some data, some program to the prover, the client, a powerful machine. And the prover is running the program on the input data, obtains some result. The statement is going to be that our evaluation is correct, that we indeed evaluated the correct program on the correct data. So that's the witness. Now the witness is public. There is no secrecy. It sends the proof to the verifier and the result. And then the verifier now can check and can make sure that the prover has indeed performed the service that it was contracted to do. So that's it for the introduction for on what can we prove. But in general, we can prove very complex languages, but not extremely complex languages. Still expressive enough, and we're talking here about layer 2, and we're interested in modeling the state transition of the Ethereum EVM machine. So if we want to go from state 1 to state 2, we can imagine this as a transition function. And what happens on layer 2 zero-knowledge rollups is that this transition function is being arithmetized, and then we compute a proof that this arithmetization was correct. And now the gain that we get is that not all the nodes will need to perform the transitions in the protocol themselves. Instead, they can just check the proof and make sure that this transition happened properly according to the specifications, just as in the previous, similar to the previous example. The operations will happen now on layer 2, and in order to return to layer 1, we will have to certify this updated state using the proof. And the certification is going to happen through a smart contract on layer 1, which will contain the verifier of the proof system. So I want to give you an example of how arithmetization looks like, and the one I picked is a toy one for accounts, for account transfers. And but before that, let's see what we want to get. So we want to be able to transform this Ethereum state function into a series of columns, so a series of vectors, which will be seen as polynomials, and relations, constraints among these columns. So we just want to look at how we would arithmetize this simple function, the transfer. And you can imagine, for example, you have like a sender balance where the balance remains the same, and then at the time of transfer, we lose the amount and we lose the gas, and then we stay constant again. This is then going to be a polynomial P1 of x in Lagrange basis. We can have a nonce column where everything is constant, and then because we send the transaction, now the nonce increases, and then again constant. A transfer flag that basically just says, look, now I'm transferring things. A receiver balance column that is like the opposite of the sender one, except for the gas. I'm getting the amount now, and then everything stays constant. And then some gas column where I need to store the gas and maybe have different modules that ensure that computation was made correctly. And some amount column. So the kind of constraints, so as I said, the columns are seen as polynomials. I mean, here I say column, but here they look more like rows. They are seen as polynomials in Lagrange basis. And for example, I said that we want to have columns and constraints. An example of a constraint is a binary constraint. I'm just going to say, look, what I have in my column is only zeros and ones, because this is a flag column. And the polynomial needs to satisfy this relation over some limited domain. This is going to be a cycle group of roots of unity. But this is just like subgroup of a finite field. This is just a math detail. And an example of another constraint, if I want to look at the time of just after the transfer and time before, I can say, look, I want this difference to be the gas and the transferred amount. And then I can have more complex, I can model more complex relations. Here, this omega minus 1 is just a shift to the previous timestamp. And then P5 of x plus P6 of x is just the amount plus the gas. So we've seen, obviously, that doesn't model everything, because this is just like the beginning, giving you a flavor of how it looks like. But what you can infer already is that it's extremely complex, and we're going to end up with extremely large columns for such a complicated state function. But there are two advantages of seeing things as polynomials. Advantage number one is that if we use the Schwarzschild lemma over finite fields, instead of having to check these relations between polynomials at every point, you can check it only at one random point. And the second one is that we have cryptographic polynomial commitments, which allow you to give a succinct description of the polynomial and then infer, make proofs about that. And then what you're going to store is actually going to be quite short, and you don't have to have the entire thing when you reason about it. So now we're getting to the heterogeneous part, combining proof systems. What proof system should we use? And in this talk, we're going to talk about two of them. The first one is one that you probably all heard of, is Plonk over finite fields and pairings. And in this case, we're going to look at it using KZG polynomial commitments. The second one is code-based. Here, I'm going to talk about a variant that we have, that we're using in Linea, which is called Wizard plus Arcane, and the polynomial commitment is called Vortex. But it's part of the same family of code-based proof systems like Starks and Fry and all of that. And unfortunately, we will not cover lattice-based proof systems because we won't have time. So in terms of what kind of constraints, remember, we want to look at the polynomials, the columns, and we want to enforce relations among them. What kind of constraints can we support in this wizard system that we have? We have the typical ones. We have lookups, for example, where we say all the entries of a columns are included in another column. Permutations, all two columns are the same up to different order. We can have local constraints where we're just arguing about specific points. This is very useful when you're saying, oh, look, this column starts from 0. This account just got initialized, 0 balanced, something like that. And global constraints where I'm talking about what happens over the entirety of the polynomials. And this is the one that we've just seen, where the polynomial gets shifted, and on the right side I have amount plus gas. And this language is well suited for writing arithmetization constraints, and the code-based proof system is also going to be quite well suited for checking these constraints efficiently. So what are the characteristics of this proof system? We have high parallelization because we use a hash function that is based on lattices, and then the codes that are used are Ritz-Solomon codes, which are linear. So then in the end, we end up with all the operations being linear or close to linear. So it's easier to linearize them and parallelize them. And then, and the circuit size is going to be slower than in the case of Plonk. So it's easier to really go through a very, very large number of polynomials and constraints. But we have some drawbacks. The first one is that the proof size is going to be larger than the one of Plonk, and the verifier time is also going to be slower. Now let's look on the other side at Plonk circuits. So now we're using pairings, elliptic curves. Here the circuits are at the base level. They are arithmetic circuits, addition and multiplication gates, fan into and unlimited fan out. That's how they look. And we can obviously define more gates. We can have lookups, we can have permutations, but mathematically, when we write these complex gates, it seems that they are less compatible with the arithmetization than the code-based ones. Obviously, this is not a constant. Maybe someone will come up with better solutions in the future, but this is the situation right now. So what are the characteristics of Plonk? We're going to have small proof size, much smaller than Wizard, Arcane, and Vortex. I have a complex name for it, but I think we need a short one. So much smaller than the code-based proof system, so it's more suitable for publishing the proof to the layer 1. And the verifier time is also better. It's a smaller verifier circuit, which again means that it's better for layer 1, shorter to verify, and also the smart contract is going to incur less costs, which is quite crucial. But the problems are, it's really almost complementary. Larger prover time, it takes a long time to process a large number of constraints, and also the prover circuit grows a lot than in the code-based proof system. So now the question of the talk is, can we use the advantages of one proof system to offset the disadvantages of the other? And the answer is yes, and it's by using recursive proofs. So complicated name, but it just means you do a wizard proof followed by a Plonk proof. What is going to be the language? So for the wizard proof, we're going to have the short commitments to the arithmetization columns. The statement is going to be my columns satisfy the constraint system. The witness is going to be the columns themselves. I get my wizard proof. And then for the Plonk prover, I'm going to commit to the wizard proof, yet another commitment. And of the statement, the new statement, the new ZK, new proof statement is going to be that this proof, this P-wizard satisfies the wizard verifier circuit. That's the new language. And then the witness is going to be the proof itself. We get another proof, the Plonk one. Obviously, in your system, probably such a simple thing will not be secure. We're probably going to need public parameters, more complicated machinery. But this is a toy example. This is the core idea. And the verification is going to be only one invocation of the Plonk verifier, because it's going to automatically have also the wizard verifier circuit somewhere there inside. So we call this wizard in Plonk because it's an iteration of wizard followed by one of Plonk. We're going to have small proof size. This is going to be guaranteed by the fact that there is a Plonk layer at the end. There's going to be a better verifier time, again, because of the Plonk layer at the end. And now we also have good prover time, because when we get the huge heap of arithmetization columns, these get parsed initially by the wizard, which gives them to a manageable size. And the circuit size, again, is going to be smaller because this initial very hard part for the prover is being taken care of by the wizard layer. Yeah, and the circuit size, as I said, yeah, I'm just repeating myself. Okay, so I have a small toy example, which is linked MIMC hashes. And in this small example, I'm just going to hash a vector. So initially, I start with the state of 0. I hash the first element to get my first hash. And then I'm going to use that hash as the new state for the next one. So H2 is going to depend on H1, H3 on H2, and so on. So that's my circuit, and I'm going to reason about this. So what are the results if I'm trying to compare Plonk wizard and Plonk and wizard on this very small thing? At very small column sizes, Plonk performs much better than both wizard and wizard and Plonk. But again, we live in the world of the EVM. So we have huge column sizes, hundreds of millions. What about those? And I have a benchmark for linked MIMC. So we can see the orange is just the code-based thing. It performs the best, but we say, okay, this is not an option because the proof size is too large to put on layer 1, and also the verification time is too large. Then we have Plonk, which at the beginning, on the left side before the graph starts actually, is the best one out of everyone. Then as time passes, it's better than this cyan line, which is wizard and Plonk. But as we increase the column size, it becomes really, really impractical to parse, to run the Plonk prover. And you can see that the combination of the two proof systems really stays somewhere in the middle, actually closer to the bottom, at least for this toy example. So it looks like we're really getting the benefits of both proof systems. And in terms of the verifier benchmark, for this particular example, it doesn't really make sense, but just because of the way the circuit seems to behave. But what I can say is that the verification time is not impacted. And I'm almost done. I just want to say a few words about other implications of combining your proof systems. One is trust assumptions. A code-based proof system, like the one with pluses here, has transparent setup. That's super nice. Plonk, on the other hand, has trusted setup, so we need a trusted ceremony to make it work. But there are also others. And what I want to say is that when you combine them, you're going to get the worst assumption, as usual in crypto. And there's some other special cases to consider. For example, Plonk is really fast for some precompiles. And these are generally the elliptic curve operations. So for ECMule, ECPair, ECAD, our implementations have very hand-optimized solutions for this. And Wizard cannot compete. So the takeaway now is if you have a very complex system, it might make sense to use a bigger stack. More complexity might give you lower costs, lower latency, lower everything you want. But it's not always the case. If you have a simple system that doesn't have to deal with these huge sizes, then maybe you can do your benchmarks and see, oh, this proof system is actually satisfies all my needs and is even the best at this particular size. And future directions that one can ask is, do lattice proof systems also have like a particular niche where they are better than the elliptic curve one, than the pairing ones and the code-based ones? And also like for aggregation, which one is the best? I guess we can have an entire talk about that. And that's it. Thank you for your attention.
Wonderful presentation, Bogdan. Thank you so much. Do we have any questions from the audience today? Okay, great. Mike over here.
Hey, thanks for the presentation. So if I understand correctly, you use Plonk to verify Wizard.
Yes.
Right? So since you have well-defined problem at the beginning, right? So the verification of the Wizard proofs, would it make sense to basically use the old good Graph 16, which is even faster and smaller?
It's a good question. I'm not sure I can answer it fully, simply because I haven't. What I can say is we used to use Graph 16 at some point in our stack, and as time passed, now we don't. I mean, we still have the implementation of it, but we don't use it at least for our layer 2. I cannot really tell you the reason, but there is one.
Right, but yeah, but you don't want to change the wizard, right? Like once you have it. Yeah, but then you don't do it every day. If you do it like once a year, then you deploy a new verifier, and that's fine.
No, but if you use Graph 16 to generate the whole trusted setup.
Sure, yeah, but there is the whole initiative, right, to use this double stage ceremonies, so you can benefit from it. I mean, again, it's I think how often you want to do it. And then, at the end of the day, we want to have we should be able, yes. What we need to optimize in ZK for a real-world adoption is to have very fast proofs to generate.
First, secure. Then.
Oh, obviously. Yeah.
Awesome. Any other questions? Yep, over here. Oh, nice catch. Okay.
Did you compare it with something like air/fry?
So for this, I haven't myself, but I think in general the team usually whenever something new comes up, they always check it. So I'm pretty sure some other people did before me.
Comparing with Plonk was not fully fair, but
Yeah, I completely agree, and it's something that I meant to say. Also, like the circuits are not even the same, right? Like, I mean, there are multiple ways of writing one. I completely agree with that, yeah. The point was not that. The point was more we have to keep an open mind and combine things. Maybe having a complex stack can really save us.
Anyone else? Okay, thank you. Our next presentation will go live at 12:35. Thank you.
Thank you.